We already heard yesterday and today on the Connecta project. Janos Valderverdien worked on it already from last century. Can you please give an update on Connecta?
Yeah, good morning, ladies and gentlemen. So we just saw a lot of theory about the TSN. One subject of the Connecta project was also to apply those technologies in a next generation communication network. And this is what my presentation will be about. So this was about my person. So in the Connecta project, I was the working package leader for this drive by data concept. And so what means drive by data? So drive by data defines the onboard communication system for next generation trains. Yeah. And so drive by data has been developed as a part of the Connecta project. Connecta project is more than just drive by data. So this was just one working package inside Connecta. And of course, we also have a companion project in Shift to Rail, which was called Safe for Rail, which contributed to the specification and also contributed to the providing the prototypes for this network. So next slide, please. So why do we need drive by data? So the vision is that in future we will have a full electronic system, so removing all the hydraulic, pneumatic, mechanical stuff as much as possible. And therefore we have to improve the existing network technologies. First of all, of course, we have to improve in the direction of to have a more robust system. We also have to face the fact that in future we will have more mixed criticality traffic using the same network infrastructure. So on the one hand side, we have more comfort-related functionality. On the other side, we might have really safety-critical data communication. All this must be possible. Then our very special, I would say, network property, which we have in train, so that we have a dynamic train-wide network. So typical situation, if you are coupling to trains, then you are coupling to networks. But after coupling, as soon as possible, everything should work as before. And this is something which we do not encounter in other industries. And it finally also, I already mentioned it, so about the safety functions. So the ambition is to support safety functions up to a SIL level of 4. Next slide, please. State of the art, just to mention it. So presently we have this TCN standard series, so the IEC 61375, which defines a couple of network technologies which are used in today's trains. And we took this as a basic, but we enhanced this with specific functionalities. So next slide, please. So here we have some bullet points which are listing what is new with the drive by data concept. We will see it quite soon in the next slide that we have now 2 data transmission planes for time and mission critical data, that we are using this TSN technology, which we saw in the presentation before, a subset of this. So in this form, we are paving a way also for a railway-specific profile of TSN. Then the network is responsible for basically 2 safety functions. The first one is the safe train inauguration, so the determination of the train setup, the train composition, the sequence of the vehicles, the orientation of the vehicles. So this is highly safety related, and also a specific protocol for end-to-end data communication in a safe manner. And as an addendum, also we investigated about the possibility to have wireless communication besides the cable-bound communication which we are using today. Next slide, please. So here we see the architecture. So we see on the upper part and the lower part, there's ETB line A and B, which is a communication system throughout the train. And inside each vehicle, or we call it consist here, We have a local network, which is the Ethernet consist network, which is nowadays typically in a ring structure for redundancy reasons. And on this train level, we have a line structure. Yeah. And what we did in order also to support there's in future high deterministic data traffic, we logically separated this network in two planes. So we call it the left plane and the right plane. So this is a logical separation using virtualization of the communication. Yeah. And this allows, it's indicated here with those arrows here, this yellow and red arrows, for data critical traffic to transport it in parallel over both planes. So those two planes are independent from each other. So if we have a failure in one plane, we still have the other plane available for data communication. So this allows to give us even less redundancy, at least for critical data. So critical data is produced by end devices and then sent over both planes, yeah, using TSN technologies in that case, yeah, and sent to the destinations. And in order to use TSN, we also, this is indicated with this clock symbol here on the top. So we need to have time synchronization inside the train. Yeah. This is especially needed for this, for this scheduled traffic, which is one of the technologies which is provided by the TSN. Next slide, please. So what are the key benefits of this new approach? So of course, support of TSN, time-sensitive networking for a deterministic data exchange. Seamless redundancy of time-critical data, this I already mentioned. The ambition is to reduce the train lines as much as possible. So in trains today, we encounter quite a lot of different train lines. So the ambition is to reduce this to the minimum number of train lines in future and to replace it everything by data communication. Then next was to achieve a high reliability by using this independent, logically independent communication planes. But on the other hand, we still need to be compliant to existing architectures. So, and as you saw in the picture before, this architecture picture, this basically is more or less identical to the existing communication systems. Yeah. So that means for all legacy applications, it can be used as is, though they will not see any difference to the situation before, but only the new applications which require a high deterministic data transmission, they make use of this virtualization of these two planes. So that's a basic difference. Then in order to support the safety functions, we have an intrinsic consist orientation detection. I will come to that later on. A bypass function is something special. So if we have a failure in one of the net or train backbone nodes, so we need to bypass in order to continue communication. It was a decision here in the project to remove those bypass functions. And okay, fire protection support. I think this is also something to mention. Next slide, please. Okay, here just a picture. I go not to the details here. So this is just a selection of the IEEE standards about TSN, which we are using here in our future system. Next slide, please. The first safety function, which I already mentioned for the network, is a safety integration. So basically, the principle here is so that the twin backbone nodes, they determine first the network topology and derive from that the train composition. Train composition means the sequence of the vehicles and the orientation of the vehicles. And by this, we also can support a train integrity function, so to check the train integrity. And in order to achieve a high safety integrity level with that, we need to have what we call an validation of this integration result. So integration itself is performed by the train backbone nodes, but an independent computer is performing validation of this train backbone, of this train integration result by using independent sensor information. So this is an important part, so that we have an independent check of the integration result. Next slide, please. The safe data transmission protocol. So this is end-to-end communication in a safe manner. Though here, basically, we took that what was already existing. So this was this STDV2, Safe Data Transmission version 2 protocol, which is already a part of the TCN standards, and just improved it. So that this protocol is in future also able to support functions or a data transmission up to SD level of 4. This STDV2 protocol was only able to support up to a level of still 2. So next slide please. Just to mention it, as I said at the beginning, we also investigated wireless technologies. So here, a replacement of the train-wide communication with a wireless technology based on LTE. And for supporting this train integration function, we also added this RFID. So this RFID is then used to determine the correct sequence of vehicles and orientation of vehicles. And once this is established, then we can establish a safe communication between the different vehicles of a train. Next slide, please. So something similar, but here now on consist level. So on consist level also in future, the intention is to have devices connected wirelessly. This will for sure not be valid for all devices which we want to connect, but for selected devices. And here we worked with railway certified Wi-Fi systems, but also checked the possibility to adopt TSN technology. So presently there's also work or standardization work ongoing to introduce TSN principles also for wireless communication. And this is something which we also pursued here. Next slide please. State of implementation. So in Connecta, so we built up 2 technical demonstrators. The first one resembling a urban train. The second one a regional train. So regional train, there are also 3 main companies contributing to Connecta were present and contributing. So Alstom, CAF and Siemens. You see here on the bottom picture of this regional demonstrator. Of course, this was just a lab demonstrator. You see there's a lab setup. And next slide, please. Just to report about some experience which we gained so far in this work. The first thing, of course, is about TSN. Though TSM, we saw it in the presentation before, is something still ongoing. So not all standards are finalized so far. So this also produced some delay in our work. Then also mentioned, so we have some specialties in the railway field. So we have these dynamic networks, which we don't have in other industries. And especially when we saw that this is a problem, especially when it comes to adopting this scheduled traffic from TSN. As a problem which we encountered was really to get a train-wide clock synchronization. We saw that this is a quite slow process when we are coupling to trains. So we decided then to use this scheduled traffic on consist level and on train backbone to use other TSN technologies. Next slide, please. Our implementation test phase. Okay, some experience. So of course, as usual, more complex than anticipated. Configuration took longer. We could not execute all defined test cases, but this was mainly motivated by this COVID-19 situation. You saw we 3 companies working together and connecting a network together. Of course, you have to do in a workshop commonly, but this was not possible. So what we did, so we installed an LTE bridge between the different sites across Europe. But you can imagine, though, real-time communication was suffering from that, yeah, and also we had only one communication channel available, so we also could not test the redundancy. But we hope that this can be then in the final phase of the project be repeated in a real version. Next slide, please. Outlook. So we are now have entered the final phase of Connecta. And the idea here is to increase the technical readiness level. Yeah, and this means, first of all, that we that we use real products. Yeah, and also we'll have a real test train available where we can test a part of those principles. Then we also have to add cybersecurity aspects to this. We also have to look to upcoming technologies or like FIMCS and CCS, and to see how to interface with our system. Yeah. And finally, of course, it will be a matter of standardization. So we have to improve our existing standardization at those technologies to those the related standard parts. So next slide, please. Okay, so this I think is the final one. Some additional information where you can get more details about that what we did. So not only about the 12 data, what we did in general in the Connecta project. And also you can also download open publicly available specifications about the network. Okay, so that's all. Thank you for your audience.
Thanks a lot.